Sognefjord, Norway, 895. While Frankish shipbuilders complete war galleys in 6 weeks using animal fat and beeswax, Viking tar maker Bjorn Stumpfoot spends 3 months burning pine stumps in smoking earthen kilns. His neighbors call it wasteful madness. They call him obsessed with primitive methods. He produces thick black tar from resinous stumps when everyone else uses quick, economical waterproofing that works perfectly for coastal waters. His process consumes massive fuel for just 50 gallons per week, when standard techniques finish ships in hours, not months. Then the North Atlantic called. 2,000-mile voyages to Iceland, 900-mile passages to Greenland, distances that destroy every European vessel. Ships with conventional waterproofing failed within 500 miles, hulls cracking, seams separating, taking on deadly amounts of freezing water. But Bjorn's tar-soaked longships? 10,000 miles without major hull repairs. Wave after wave, storm after storm, his primitive preparation kept crews alive where modern efficiency meant death. What did he understand about wood preservation that every maritime expert missed? If you value stories of medieval techniques that defied impossible odds, make sure to subscribe. We've got more documented accounts worth discovering. The autumn mist clung to Sognefjord's dark waters as Bjorn Kolson hefted another pine stump from his growing pile. Along the shoreline, shipyards buzzed with activity as neighboring craftsmen raced to complete their vessels before winter's grip tightened. Gunnar Eriksson's yard had already launched 2 longships since midsummer, their hulls gleaming with fresh applications of heated beeswax and animal tallow. The scent of warm pitch drifted across the water as crews applied final coats to oak planking, sealing joints with methods proven across generations of coastal raiding. Bjorn's operation looked markedly different. Where others worked with economy and speed, he had spent the better part of 3 months accumulating what his neighbors dismissively called fuel wood. His selection process alone baffled local shipwrights. While they gathered any available timber for construction, Bjorn sought only the most resinous portions of ancient pines, the stumps left behind by long-dead giants, and the gnarled root systems that required dangerous excavation from rocky hillsides. Each piece demanded careful examination, his weathered fingers probing for the telltale stickiness that indicated high resin content. The conventional approach made perfect sense to everyone else. Animal fats rendered from cattle and sheep mixed readily with oak gall, creating waterproof compounds that could be applied hot and set quickly. Beeswax, when heated to proper consistency, sealed wood fibers effectively and remained pliable in moderate temperatures. Imported pitch from Frankish territories provided another reliable option, brushed on warm and hardening to create barrier layers that kept water from penetrating hull planks. These methods had supported Norse coastal operations for decades, enabling raiders to strike quickly across the North Sea and return before seasonal storms made voyaging impossible. Bjorn's earthen kilns represented an entirely different philosophy. Where others measured construction time in weeks, he planned in seasons. His kilns themselves took days to construct properly, requiring precise engineering of air channels and collection systems that his grandfather Ulf had taught him according to specifications passed down through countless generations. The old man insisted on exacting standards, the internal chamber dimensions, the angle of the collection trough, the spacing of ventilation holes, all critical to achieving the controlled combustion that separated resin from wood without destroying the valuable compounds through excessive heat. The chemistry underlying his process remained invisible to casual observers, but governed every aspect of the operation. Pine stumps contained 15 to 20% resin compared to the mere 2 or 3% found in branches and younger wood. This concentration resulted from decades of resin accumulation in heartwood, creating dense deposits of compounds that standard timber lacked entirely. The earthen kiln's design maintained temperatures between 500 and 600 degrees, hot enough to liquefy these resins without reaching the combustion point that would reduce them to ash and smoke. Most critically, the oxygen-starved environment within the sealed chambers prevented the resin from burning while allowing thermal extraction. As pine stumps slowly carbonized over 5 to 7 days, volatile compounds distilled away while heavier resin fractions collected in the stone-lined channels Bjorn had carved around each kiln's base. The process demanded constant attention, adjusting airflow, monitoring temperature through subtle changes in smoke color, timing each phase according to ancestral knowledge that recognized optimal extraction points through sensory cues modern craftsmen had forgotten. Gunnar's mockery carried the weight of practical authority. His shipyard employed 20 craftsmen using techniques learned through trade connections with Frankish and Anglo-Saxon maritime centers. His vessels reached completion in predictable time frames, enabling crews to depart for Britain's coasts while sailing weather remained favorable. The economic logic seemed unassailable. Why consume months of labor and massive quantities of fuel wood to produce what appeared to be the same black sticky substance that imported pitch provided at far lower cost? The social pressure intensified as Bjorn's kilns continued smoking through the autumn months. Neighbors questioned his judgment openly, pointing to successful expeditions launched using conventional waterproofing methods. Local jarls wondered whether resources might be better allocated to additional vessels rather than excessive preparation of single ships. Even among his own family, doubts emerged about the wisdom of following ancient practices when modern efficiency offered clear advantages. Yet Bjorn persisted according to knowledge his lineage had preserved through 3 centuries of Norse shipbuilding. His grandfather's teachings emphasized patience and precision over speed and economy. The old tar master had learned from his own grandfather, who had learned from his, creating an unbroken chain of technical knowledge stretching back to Mesolithic forest peoples who had developed these techniques over 10 millennia. Each generation refined the process slightly while maintaining core principles that prioritized deep wood penetration over surface protection. By late autumn, Bjorn's stockpile had grown to encompass 4 to 6 tons of pine stumps per longship, a massive investment that neighbors calculated could fuel entire households through the coming winter. His kilns produced the thick black tar in 50 to 80-gallon batches, each requiring a full week of constant tending. The final product differed noticeably from standard sealants in consistency and penetration capability. Soaking deep into oak fibers when applied warm at 80 to 90 degrees, rather than forming surface layers that quick cooling pitch created. The application process itself demanded multiple coats applied over weeks rather than days. Each layer needed to penetrate 5 to 8 millimeters into wood fibers before the next application, creating layered barriers that progressively sealed every microscopic gap in the hull's surface. By winter's end, Wave Serpent carried 130 gallons of tar worked deep into every plank, rib, and joint, an investment that seemed absurdly excessive for coastal raiding but represented careful preparation for voyages that stretched beyond conventional limits. As spring approached and ice began breaking up in the fjords, the stakes of Bjorn's gamble became clear. While Gunnar's fleet prepared for familiar routes to Britain's shores, Wave Serpent's crew had set their sights on Iceland's distant coast, 2,000 miles of open North Atlantic that had claimed every vessel attempting such distances with conventional European waterproofing methods. Summer 896 brought fair winds and calm seas as 3 distinct fleets prepared for departure from Norwegian fjords. Gunnar's vessels, sleek and efficiently constructed using proven Frankish techniques, loaded provisions for Britain's familiar coasts. Their hulls gleamed with fresh applications of heated beeswax and animal tallow, waterproofing methods that had served Norse raiders reliably for generations of coastal expeditions. Anglo-Saxon influenced ships from competing yards carried similar preparations, their crews confident in traditional sealants that had withstood countless voyages across the North Sea's predictable waters. Wave Serpent presented a stark contrast as Bjorn's crew made final preparations for their ambitious Iceland expedition. The vessel's dark hull showed the deep saturation of months of tar application, each plank penetrated to depths that conventional waterproofing never achieved, while neighboring ships carried standard provisions for raids lasting weeks. Wave Serpent's hold contained supplies for a journey measured in months across waters that had claimed every previous attempt at such distances. The initial departures proceeded according to established patterns. Gunnar's fleet caught favorable currents toward Britain, Their destination a mere 300 miles across familiar shipping lanes that Norse navigators had traveled for decades. The Anglo-Saxon influenced vessels set course for Irish waters, attempting crossings of 400 miles maximum before reaching safe harbors where repairs and resupply could address any waterproofing failures. These routes represented the practical limits of European maritime technology, distances that allowed for emergency beaching when hull integrity began failing. Wave Serpent's course traced a far more ambitious arc toward Iceland's distant shores, 2,000 miles of open North Atlantic where no safe harbors existed, and where emergency repairs meant certain death in waters too cold for human survival. The route demanded absolute confidence in hull integrity across distances that exceeded every known limit of wooden ship construction. Within the first weeks of the expeditions, disturbing reports began filtering back to Norwegian coastal settlements. Frankish-built vessels operating in the English Channel encountered hull deterioration that forced premature returns to friendly ports. The animal tallow and oak gall mixtures that had seemed adequate for short, coastal hops began failing when exposed to extended saltwater immersion. Planking showed separation along sealed joints as the organic compounds broke down under constant wave action and salt spray penetration. The Anglo-Saxon-influenced fleet fared no better in Irish sea conditions. Beeswax applications that provided effective short-term waterproofing began cracking and separating when subjected to the thermal cycles of extended voyaging. Daytime heating, followed by nighttime cooling, created expansion and contraction stresses that rigid surface sealants could not accommodate. Crews found themselves beaching every 200 miles for emergency resealing operations, turning what should have been direct crossings into series of desperate repairs. Wave Serpent, meanwhile, pushed steadily westward into conditions that revealed the fundamental inadequacy of conventional European maritime technology. North Atlantic temperatures dropped to 35 degrees Fahrenheit, well below the flexibility range of standard sealants. Where beeswax became brittle and shattered along plank seams, Bjorn's pine tar remained supple and adhesive. The phenolic compounds extracted through his ancestral process maintained their protective properties across temperature ranges that destroyed every contemporary waterproofing method. The ocean itself became an implacable testing ground for competing technologies. Massive swells generated by Atlantic storm systems created hull stresses that no coastal voyage had prepared European shipbuilders to address. Conventional waterproofing, designed for the relatively gentle flexing of North Sea conditions, failed catastrophically when subjected to the violent hull movements that 10-foot swells demanded. Surface coatings cracked and peeled away as oak planking twisted under forces that exceeded every previous engineering assumption. More insidious than immediate structural failure was the gradual infiltration of salt water through compromised seals. Standard European vessels showed water intrusion rates that crews could initially manage through constant bailing, but the problem compounded exponentially as failed waterproofing allowed deeper penetration into wood fibers. Salt crystallization within the wood structure created internal pressure that split planks from within, turning minor sealing failures into catastrophic hull breaches that could sink vessels within hours. The marine environment itself presented challenges that coastal European shipbuilding had never encountered. Shipworms, boring mollusks that consumed wood faster than crews could repair damage, thrived in the warmer waters that conventional vessels carried within their compromised hulls. These organisms, dormant in cold surface waters, multiplied rapidly once they gained access to the warm, moist environments that failed waterproofing created within hull cavities. Wave Serpent's tar-impregnated hull demonstrated the superiority of deep penetration preservation across every challenge the North Atlantic presented. The resin compounds that Bjorn's process had driven 5 to 8 millimeters into oak fibers, created barriers that remained effective even when surface layers experienced wear. Multiple applications had built redundant protection systems where the failure of outer tar layers still left deeper impregnation intact and functional. Most critically, the pine tar's natural antiseptic properties killed shipworms on contact, preventing the hull-destroying infestations that crippled vessels using organic sealants. The phenolic compounds that traditional Mesolithic extraction had concentrated proved toxic to marine borers while remaining harmless to human crews, creating biological protection that no European maritime technology could replicate. After 500 miles of North Atlantic voyaging, the distance that typically marked the failure point for Frankish-style vessels, Wave Serpent showed minimal water intrusion despite encountering conditions that had destroyed every previous long-distance attempt. Hull inspection revealed the tar's penetration, maintaining its protective barrier at depths that surface coating methods never achieved, creating wood resin composite materials that proved stronger and more durable than either component alone. By the time Wave Serpent had covered 1,000 miles, twice the maximum distance that conventional European ships could survive continuously, Bjorn's crew began to understand the full magnitude of their technological advantage. The primitive tar-making process that neighbors had dismissed as wasteful inefficiency had achieved what the most advanced European maritime engineering could not: creating wooden vessels capable of oceanic voyaging across distances that redefined the possibilities of medieval exploration. Iceland's eastern coast emerged from the mists after 23 days of continuous sailing, an achievement that redefined the boundaries of medieval maritime possibility. Wave Serpent had covered 2,000 miles of open North Atlantic without the hull failures that destroyed every previous long-distance attempt. Eric Bjornsson's navigation had proven flawless. But more importantly, Bjorn's tar-impregnated hull had withstood oceanic conditions that no European vessel had survived continuously. The crew's examination of their vessel revealed the full extent of their technological advantage. Where conventional ships would have shown catastrophic hull separation and uncontrollable water intrusion, Wave Serpent's planking remained tight and dry. The tar's deep penetration had created a wood resin composite that flexed with wave action rather than cracking under stress. Surface wear was minimal, and more critically, the protective barrier extended far enough into the wood fibers that surface damage did not compromise the hull's integrity. Most European maritime experts would have declared the Iceland voyage impossible with available technology. The distance exceeded every known limit of wooden ship construction, requiring hull integrity across conditions that had claimed countless vessels attempting far shorter passages. Yet as Wave Serpent's crew replenished their water supplies from Icelandic streams and repaired minor rigging damage, they contemplated an even more audacious objective. Greenland lay 900 miles further west across waters that presented the harshest marine environment on Earth. No European vessel had attempted such a passage and survived to report the conditions they encountered. The route pushed beyond established limits into oceanic regions where rescue was impossible, and where any significant hull failure meant certain death in waters too cold for human survival longer than minutes. The crew's decision to attempt the Greenland passage represented ultimate confidence in their vessel's capabilities, but the wisdom of that confidence would be tested by conditions that exceeded even North Atlantic standards of brutality. Greenland's coastal waters remained near freezing throughout the summer months, creating thermal stresses that shattered conventional sealants within days. Massive icebergs, some larger than entire Norwegian villages, drifted south from the Arctic ice cap, their underwater portions capable of crushing wooden hulls like eggshells. Pack ice presented perhaps the most insidious danger, grinding against ship hulls like millstones as currents compressed floating ice fields into solid barriers that could trap vessels for months. The ice's abrasive action scraped away surface protection with relentless efficiency, exposing underlying wood to saltwater penetration that conventional waterproofing methods could not prevent. Ships using standard European technology would find their hulls compromised within hours of entering pack ice regions. Wave Serpent's departure from Iceland marked the beginning of the most demanding test any medieval vessel had faced. The initial days of westward sailing revealed conditions that would have spelled immediate doom for conventionally waterproofed ships. Surface temperatures dropped to levels where beeswax became glass brittle and animal fats crystallized into useless residue. The thermal cycling between day and night created expansion stresses that rigid surface coatings could not accommodate without cracking and peeling away entirely. European ships attempting similar passages failed according to predictable patterns that Bjorn's crew could observe in their imagination. Hull planks separated as rigid sealants lost adhesion in sub-freezing conditions, allowing salt water to penetrate wood fibers that had never been properly protected. Water intrusion that began as manageable seepage quickly became torrential flooding, as failed waterproofing allowed deeper penetration into structural timber. Most critically, water trapped within hull cavities froze solid, expanding with irresistible force that split weakened timbers and opened catastrophic breaches. Wave Serpent's tar-penetrated hull adapted to these extreme conditions through the molecular flexibility that Bjorn's ancestral process had created. The resin compounds remained pliable at temperatures of -10 degrees Fahrenheit, flexing with hull movement rather than shattering under thermal stress. The deep penetration of protective compounds meant that surface wear from ice abrasion did not compromise the barrier's effectiveness, as layers of protection extended 5 to 8 millimeters into the wood structure. Pack ice encounters that would have destroyed conventional vessels became manageable challenges as Wave Serpent's hull proved capable of withstanding grinding contact with ice formations. The tar's natural lubricity reduced friction between ice and hull, while the resin-hardened wood surface resisted the gouging that typically opened seams in unprotected planking. Even when ice scraped away surface layers of protection, the deep impregnation ensured that effective barriers remained intact beneath. The biological protection that pine tar provided proved equally crucial in Greenland's waters. Marine organisms that survived in these harsh conditions possessed remarkable destructive capabilities, boring through compromised wood with efficiency that could sink vessels within days. Wave Serpent's antiseptic tar coating killed these organisms on contact, preventing the infestations that turned minor hull damage into catastrophic structural failure. After covering the 900 miles to Greenland's coast, Wave Serpent had achieved what medieval maritime technology was not supposed to accomplish. 3,000 total miles of oceanic voyaging had tested every aspect of the vessel's construction, subjecting Bjorn's tar-protected hull to conditions that exceeded the survival capacity of every contemporary European ship design. The successful landing on Greenland's rocky shore represented more than geographical exploration. It demonstrated technological capabilities that redefined medieval maritime possibilities. Hull inspection revealed the tar barrier intact after exposure to conditions that would have destroyed conventional waterproofing within the first few hundred miles. Wood fibers remained impregnated with protective compounds that showed minimal degradation despite month-long exposure to salt spray, ice abrasion, and thermal cycling that shattered every known sealant. The magnitude of Wave Serpent's achievement became clear when measured against European maritime limitations. While the most advanced continental shipbuilding rarely produced vessels capable of more than 500-mile coastal voyages, Bjorn's tar-making process had enabled continuous oceanic travel across distances equivalent to crossing the Atlantic twice. The technological gap was not incremental improvement, but fundamental transformation of what wooden ships could accomplish. The primitive process that Norwegian neighbors had dismissed as wasteful fuel consumption had achieved 10,000-mile voyage capability, opening oceanic routes that connected continents and established the foundation for exploration networks that would reshape medieval understanding of global geography. Word of Wave Serpent's impossible journey reached Norway's coastal settlements through networks that carried news faster than ships could sail. Returning traders brought accounts of the vessel's successful Greenland landing, stories that initially met with skepticism until corroborating reports arrived from multiple sources. The ship that neighbors had mocked for its excessive preparation time had achieved what every maritime expert had declared impossible with available medieval technology. Gunnar Eriksson found himself among the first to acknowledge the magnitude of his earlier misjudgment. His own vessels, despite successful completion of familiar British raids, had never ventured beyond the 500-mile range that represented European maritime limits. The revelation that Bjorn's primitive tar-making process could enable 10,000-mile voyages forced a complete reevaluation of conventional shipbuilding wisdom throughout the Norwegian coastal communities. The transformation began with individual shipwrights seeking apprenticeships at Bjorn's tar production sites. Men who had dismissed stump burning as wasteful inefficiency now offered substantial payments for instruction in the ancient techniques that Ulf the Ancient had preserved through generations of oral tradition. The knowledge that seemed primitive revealed itself as sophisticated industrial chemistry developed over millennia of empirical refinement. Within 2 years of Wave Serpent's return, archaeological evidence reveals the rapid spread of Viking tar-making technology throughout Scandinavia. Production sites emerged across Norway's fjord regions, each following kiln designs that Bjorn had perfected according to ancestral specifications. The Bergen district alone supported 12 major tar operations by 900, their smoking kilns visible for miles as they processed the massive quantities of pine stumps required for long-range fleet construction. The scaling of production represented a fundamental shift from individual craft practice to regional industrial capacity. Sites near Trondheim produced 500 gallons per season, supporting entire fleets of exploration vessels that could attempt the Greenland route without risking catastrophic hull failure. The Stockholm region developed operations that exceeded 1,000 gallons annually, creating surplus production that enabled tar export to neighboring kingdoms desperate to match Norse maritime capabilities. Thorvald Shipmaster's operation in the Trondheim district exemplified the industrial transformation that Viking tar making underwent. His facility employed 40 specialized workers operating 15 kilns simultaneously, processing the 6 tons of pine stumps required per longship across production cycles that maintained continuous output throughout the sailing season. The systematic approach maintained ancestral technique effectiveness while achieving commercial volumes that could support fleet operations spanning multiple continents. The military implications became apparent as Viking fleets equipped with tar-protected vessels revolutionized medieval naval warfare. While European coastal defenders expected seasonal raids limited by hull durability and weather windows, Norse expeditions remained seaworthy for multiple campaign seasons. Ships that conventional wisdom suggested should require beaching every 200 miles for waterproofing renewal instead operated continuously across oceanic distances that enabled strategic surprise across impossible ranges. Danish fleets using Viking tar technology conducted successful campaigns that struck targets from Ireland to the Mediterranean, their vessels maintaining hull integrity across distances that no European navy could match. The technological advantage translated directly into tactical superiority as Norse raiders could appear at locations beyond the defensive calculations of continental powers who assumed traditional maritime limitations applied to all wooden vessels. The economic transformation proved equally dramatic as what began as neighborhood mockery of wasteful fuel consumption became Scandinavia's first major industrial export. Stockholm tar, produced using techniques perfected through Bjorn's ancestral knowledge, dominated European naval markets by 1200. Swedish tar exports reached 100,000 barrels annually, with premium prices reflecting the product's superiority over every competing waterproofing method available to continental shipbuilders. European recognition of Viking tar superiority spread through practical necessity rather than theoretical understanding. English naval records from 1300 specify Stockholm tar for Royal Navy vessels, documenting premium payments for Swedish-produced pine tar despite the availability of cheaper alternatives. French maritime arsenals imported Nordic tar makers to establish local production facilities, though their efforts consistently failed to replicate the quality achieved through authentic Scandinavian techniques. The failure of European replication attempts reflected the complex infrastructure and generational knowledge required for effective tar production. Continental forests lacked the ancient pine stands that provided optimal resin content, while imported Scandinavian stumps proved prohibitively expensive for large-scale operations. More critically, the precise temperature control and timing required for effective resin extraction demanded expertise that could not be acquired through brief apprenticeships or written instructions. Italian naval arsenals in Venice and Genoa invested substantial resources attempting to master Viking tar-making technology, hiring Scandinavian craftsmen and importing specialized equipment. Despite these efforts, their production consistently yielded inferior tar that lacked the deep penetration capability and antiseptic properties of authentic Nordic products. The chemical complexity underlying the ancient process exceeded contemporary understanding of materials science, making successful replication impossible without complete cultural transmission of the traditional knowledge. Archaeological analysis of preserved Viking ships demonstrates the measurable superiority of authentic tar production methods. Vessels recovered from Danish bogs show tar penetration extending 7 millimeters deep after 1,000 years of burial, with wood fibers still protected by resin compounds that modern chemistry can identify but cannot precisely duplicate. The primitive technique achieved molecular-level wood preservation that exceeded every contemporary European technology and most modern preservative methods. By 1400, Viking tar-making technology had reached the Mediterranean through trade networks that recognized its essential role in long-distance maritime operations. Portuguese exploration fleets stockpiled Nordic tar for African voyages, while Spanish expeditions preparing for Atlantic crossings specified Swedish production methods for vessel preparation. The process that neighbors had dismissed as backward fuel consumption had become fundamental to European maritime expansion. The systematic adoption of Viking techniques across European naval establishments validated the technological revolution that began with Bjorn's stubborn adherence to ancestral wisdom. What had appeared as primitive inefficiency revealed itself as advanced industrial chemistry that enabled oceanic voyaging capabilities centuries before European shipbuilding achieved comparable results through alternative methods. By 1500, the transformation of Viking tar-making from neighborhood mockery to global maritime necessity reached its ultimate validation as European exploration fleets preparing for oceanic expeditions specified Nordic tar as essential equipment. Columbus's 3 ships departing Palos carried Swedish tar produced using techniques perfected 4 centuries earlier through Bjorn's ancestral knowledge, their hulls protected by resin compounds extracted from Scandinavian pine stumps according to methods that traced back 10 millennia. Portuguese explorers preparing for African voyages stockpiled Nordic processed tar in quantities that reflected hard-earned understanding of its superiority over every alternative waterproofing method. The global adoption of Viking techniques represented complete vindication of the industrial process that had seemed so wastefully primitive to Bjorn's Norwegian neighbors. Spanish fleets bound for the Americas loaded hundreds of barrels of Stockholm tar, recognizing that oceanic exploration demanded the deep wood protection that only Scandinavian production methods could provide. English expeditions seeking northwest passages carried Nordic tar as standard equipment, their success dependent upon hull integrity across distances that conventional European waterproofing could not support. 20th century chemical analysis finally revealed the molecular foundations underlying Viking tar's remarkable effectiveness, validating through modern science what empirical knowledge had demonstrated across centuries of maritime application. Laboratory examination of authentic Stockholm tar showed phenolic compound concentrations that created natural fungicides and antiseptics, explaining the biological protection that had preserved wooden hulls across oceanic voyages. The controlled temperature extraction that Bjorn's kilns had achieved preserved complex resin structures that provided both flexibility and durability, characteristics that modern chemistry could identify but not precisely duplicate. Spectroscopic analysis revealed why Viking tar penetrated wood so effectively compared to surface coatings that European shipbuilders had favored. The molecular weight distribution of compounds extracted through traditional kiln processes created optimal penetration characteristics, with smaller molecules carrying larger protective compounds deep into wood fibers through capillary action that heated application enhanced. Modern preservatives attempting to replicate these effects required synthetic additives and pressure treatment methods that primitive technology had achieved through patient adherence to ancestral techniques. Archaeological evidence provided the most compelling validation of Viking tar's superiority through preservation results that exceeded every expectation of medieval technology capabilities. Viking ships recovered from Danish bog sites showed tar penetration extending 8 millimeters deep after more than 1,000 years of burial, with wood fibers still impregnated by resin compounds that had maintained their protective effectiveness across centuries. Radiocarbon dating confirmed that these vessels had been treated using authentic Nordic methods, their remarkable preservation demonstrating the long-term effectiveness of traditional techniques. Microscopic examination of preserved wood samples revealed the cellular-level protection that Viking tar had provided, with resin compounds filling wood pores and binding with fiber structures to create composite materials stronger than either component alone. The antiseptic properties that had prevented shipworm damage remained chemically active after millennia, explaining how these ancient vessels had survived conditions that destroyed countless ships using conventional preservation methods. The industrial legacy of Viking tar making continued far beyond medieval maritime applications, supporting European naval operations through technological revolutions that should have rendered wooden ship construction obsolete. Stockholm tar production, based directly on techniques that Bjorn had preserved through traditional knowledge, reached peak output during the 1800s with annual exports exceeding 235,000 barrels. Swedish tar supported global maritime commerce throughout the Industrial Revolution, remaining essential to naval operations until steel ship construction finally eliminated demand for wood preservation technology in the 1950s. The scale of this industrial continuity demonstrated the fundamental soundness of the technical knowledge that Ulf the Ancient had transmitted through oral tradition spanning 300 generations. Production methods that had seemed wastefully primitive to 9th century observers proved sustainable and effective across more than 1,000 years of continuous operation, outlasting countless technological innovations while maintaining consistent quality standards that modern chemistry struggles to match. Modern marine archaeology laboratories study Viking tar techniques as essential knowledge for preserving historical wooden ships, recognizing that traditional methods often surpass contemporary preservation technologies. Museums worldwide seek craftsmen who understand the authentic pine tar process, acknowledging that ancient wisdom contains solutions to problems that modern materials science has not solved. The Smithsonian Institution's Preservation Department maintains detailed documentation of Scandinavian tar-making techniques, recognizing their superior effectiveness for long-term wood protection in marine environments. Contemporary wooden ship restoration projects consistently specify Stockholm tar or authentic Nordic alternatives, paying premium prices for products made using traditional methods rather than modern substitutes. The USS Constitution's recent restoration used Swedish tar produced according to medieval specifications, demonstrating that 21st century naval preservation still depends upon technological knowledge developed during the Mesolithic period and perfected through Viking maritime experience. The fundamental lesson embedded in Bjorn's vindication extends beyond maritime technology to encompass the relationship between traditional knowledge and modern assumptions about efficiency and progress. The deep resin penetration that his patient methods achieved created wood composite materials that modern pressure treatment attempts to replicate using synthetic chemicals and industrial equipment, yet rarely matches in terms of long-term effectiveness and environmental sustainability. From Greenland to Vinland, from the Mediterranean to the Baltic Sea, Viking tar-protected ships opened maritime routes that connected continents and established trade networks spanning the medieval world. The industrial sites that 9th century neighbors had dismissed as stump-burning folly became the technological foundation of European maritime expansion, enabling the age of exploration that transformed global civilization. Bjorn's stubborn adherence to ancestral wisdom had created the tools that allowed European mariners to cross oceans and discover new continents, proving that traditional knowledge, refined through millennia of empirical testing, often contains solutions that transcend the limitations of contemporary understanding and technological assumptions.